Next, we'll be talking about qualitative explanatory variables. This corresponds to chapter 6 in the textbook. And this chapter is one that I like the most because I think it's so interesting. And for me, it was kind of a big epiphany. And I think it's the chapter that starts to tie together everything we've been learning with regression with all the things that we learned about in ANOVA. As we'll see in this chapter, using qualitative explanatory variables in a regression allows us to actually perform t-tests and ANOVA. So ANOVA is actually regression, just a very cool thing. And I think it helps you to put together all the things you've learned in statistics into sort of one kind of a framework. Qualitative explanatory variables they're going to allow us to do things like a t-test in the regression framework, which I'll show you how to do, but also to do more complicated things, such as compare different regression lines. And let me show you what I mean by that. So first off, these qualitative explanatory variables allow us to cast ANOVA as regression. Right? They're really the same thing. Linear models, which is very cool. And secondly, they're going to allow us to compare regression lines. So in ANOVA, we just have qualitative variables. So what do I mean by a qualitative variable? I mean like group labeling. So for example, it could be like location. Are you in Canada or America? The United States of America. Are you in old or young age group? Those are examples where we have binary qualitative variables, just two categories. We could have multi-category groupings such as, racial groups, white, black, Latino, Asian, so forth. So those are qualitative things. We can also combine those with continuous variables that we've seen. So like age as a continuous variable, so age in years rather than just older versus young. The amount of pesticide applied to something. The duration of some treatment that's applied, so forth. This example that we're going to talk about is it's pretty simplistic, and the idea here is that imagine like we had an experiment where our y was the amount of nitrogen applied to a field. Sorry, our x was the amount of nitrogen applied to our field, and our y was the yield of corn. And let's say we did this in Illinois. Okay, so Illinois had a relationship like this, where there was some response, right, to the yield. And let's say we want to know, well, we also did the experiment in a different place. Like, let's say we did the experiment in Wisconsin. What would go red with orange? Well, blue would. Let's go with green. Let's say we did it in Wisconsin. Let's say we got a line like this. So this is Wisconsin. So we have our qualitative variable is the state. Wisconsin, or Illinois, and the continuous variable is nitrogen. What if we wanted to ask, but are these lines different from one another? Is the response of corn yield to nitrogen different in these different states? And that's what qualitative explanatory variables are going to allow us to do. So that's the big picture of motivation. I hope you can see why this might be interesting to you. Next, what we'll do is we'll just start at the basics, the simple, how we can characterize using qualitative explanatory variables as a t-test, and then we'll move up to the complex, more complex case that I just described here, where we're comparing two regression lines. Okay, so let's start with the binary predictor variables, or explanatory variables. So this is going to be the t-test as a regression. So we have a binary predictor variable, or explanatory variable. We have a binary x. All right, explanatory variable. Variable. Call it x. And x is location. And the location can either be, let's see, Illinois or Wisconsin. I'm going to try to keep these colors consistent. And our y, response, y is corn yield. So we're going to do this t-test as a regression here, and it's going to be clear, it's the independent samples t-test with equal variance. So I'm going to write that here. Independent samples with equal variance. So when we do that t-test, the form of the null hypothesis is something like mu of Wisconsin is equal to mu of Illinois. Right, so we want to check, is the mean yield, the population mean yield of corn in Wisconsin equal to that in Illinois? And our null hypothesis would say that they are equal. Versus the alternative, is that mu of Wisconsin is not equal to mu of Illinois. All right. So this is the t-test sort of structure. What we're going to do here is we're going to convert this to a regression. Using what's called an indicator variable. What is an indicator variable? So we'll define our indicator variable, x1. It's equal to 1 if the plot is from Wisconsin, that where we measured corn yield, and we'll set this equal to 0 if the plot is from Illinois. Now, it's arbitrary which one is 1 and which one is 0, but I kind of enjoy, arbitrary nationalism sometimes, and, even though I'm not from Wisconsin, I'll put Wisconsin as a 1 because everybody knows it's better than Illinois. And my heart really wasn't in that joke, so it really didn't even come off as a joke. Anyway, the point is that the indicator variable is arbitrary. Alright, so now let's form our... Whoa. I think I might have just screwed that up. Let's form our regression. So the regression is y equals beta naught plus beta 1 x1 plus epsilon, where epsilon follows a normal distribution with mean 0 and variance sigma squared sub epsilon. So the expectation of this epsilon is 0, right? Now, let me show you how this simplifies down to the t-test case. If x1 is equal to 0, so now we're talking Illinois, then we'll have this model. Y equals beta naught plus beta 1, and for all the plots where we've measured corn yield that have the identity of being from Illinois, their x1 value is 0. So we'll set this to 0 plus epsilon. So this goes to the model, simplifies because beta 1 turns to 0, y equals beta naught plus epsilon. So the expectation of y is simply beta naught when we're in Illinois, right? Because the expectation of epsilon is 0, so it simplifies just to beta naught. So what this means is that mu of Illinois is equal to beta naught. When we say mu of Illinois, we're talking about this mu of Illinois. We've expressed it as this intercept term. Now, if x1 equals 1, this corresponds to Wisconsin. Okay, so let's look at what the model would look like in Wisconsin for all plots from Wisconsin. Here, for whenever we have a plot from Wisconsin, x1 is 1, so we'll put a 1 in here. And the model looks like this. What does this simplify to? Y equals beta naught plus beta 1, because beta 1 times 1 is always beta 1, plus epsilon. So what is the expected value of our y? What is the expected value of yield from plot from Wisconsin? Well, since the expectation of epsilon is 0, it's just beta naught plus beta 1. So mu of Wisconsin is beta naught plus beta 1. So now we've taken these parameters that were from our t-test, right? Mu of Illinois and mu of Wisconsin, and we've re-expressed them in terms of the intercept and slope from a regression. So for the t-test, the initial hypothesis, right, was that mu of Wisconsin is equal to mu of Illinois. Now, in other words, mu of Wisconsin minus mu of Illinois is equal to 0. That's the null hypothesis. let's re-express this in terms of the coefficients that we have here. Now our null hypothesis can say mu of Wisconsin, so that's beta naught plus beta 1. So we've got beta naught plus beta 1 minus mu of Illinois, which is beta naught. This equals 0. Now this simplifies to, if we have beta naught minus beta naught, the null hypothesis is that beta 1 equals 0. Now the key here is that beta 1 is the difference in the means of corn from Wisconsin, growing corn yields from Wisconsin and Illinois. So, I should say, given the intercept here. So what this is saying here is that we can take a t-test which has these hypotheses. We can create a dummy variable, x1, and we can re-express our hypotheses from this to this. If beta 1 is equal to 0, then there's no difference in the means. Think about it. The mean for Illinois is beta naught, and the mean for Wisconsin is beta naught plus beta 1. So if beta 1 is 0, these guys both have the same mean, beta naught. So we can estimate the means. We fit the regression. We can estimate our means. And let's see. Illinois was orange, right? Mu hat of Illinois is simply our estimate for the intercept. And for Wisconsin, our estimate for the mean of Wisconsin is our estimate for the slope plus our estimate for the intercept plus our estimate for the slope. Now, remember that beta 1 is our change in y for 1 unit change in x. It's the beta 1 hat is the estimated change in y for a unit change in x. Alright, so let me show you a picture that might help you make a little bit more sense of what we mean by this unit change. And it's the same thing as we talked about before. Let's say you had, you have your yield data, y, which is yield, and you plot side by side the data from Illinois. So let's say Illinois has some yield like this. These are the data, the observations. Now they all have the x value of 0. So they're all right here. But they have a range of yields because there's some variability, right, in yield from plot to plot. And let's say it has the mean value like here. This is the sample mean. That's the average. And then for Wisconsin, because Wisconsin's better, of course it's going to have higher yield. Whoa. So let's have a scattering of yields. Now Wisconsin is where this x here, x1 is 1. The scattering of yields. And the sample mean, let's say, is up here. So if we were to create a line here, the slope of that line, the difference would be beta 1. Because this is a 1 unit change in x, and the rise would be beta 1. So this would be beta 1 hat, our estimate of the yield. And this value here, our intercept, I guess I should really have the axis of y be right here. This would be beta naught hat. Okay, this is our intercept. So when x is 0, that corresponds to the sample mean of Illinois, so that's beta naught hat. And when x is 1, that is beta naught hat plus beta 1 hat. That's the sample mean for Wisconsin. So again, if our estimate for beta 1 hat is 0, or we can't find significant reason, it's not statistically clear that it's different from 0, we would conclude that they have the same means.